Before I start, I'd actually like to find the data booklet that I would have given you guys. It should look like this. Only yours isn't in green. If you guys have your data books nearby, can you find this page here? It has a title that says Kinematics and Dynamics Formulas. You guys find that? I want to reference what we've learned so far. Talk a bit about those. Everybody has one of these, right? I didn't miss anybody needing one. Okay, physics is very, like I was saying a few minutes ago, physics is very repetitive in a way. Okay, we're going to learn a new formulas today, but the way you apply new formulas is the same as the old ones. You have to interpret which formula to use, and by the time we're finished here, like there's a lot of formulas. You have to be able to decipher which one's the right one for. Two, once you figure out which formula to use, you have to plug the numbers into the equation, and then once you plug the numbers into the equation, you may have to like cross multiply and divide or do some sort of algebra to solve, right? But like in a way, some kids they love physics because it's very repetitive. It's like, oh, this is more math. Some kids they hate it because, oh, this is more math, right? So I'm assuming you guys probably fall more towards the latter category of math. So, and this would be why I really, really need to stress to you guys, you need to do your assignments, you need to do your activities because that's your practice. I will help you. Like I will literally sit there and walk you through it if that's what you need, but you have to practice. Because like you don't get better at math if you don't practice it. So, anyways, here's the formulas we've learned so far. Here's a couple. Velocity is distance over time. Or actually, the first one is speed is distance over time. The next one is velocity is distance over time. Here's one involving acceleration. Then there's a couple right here involving force. Can I highlight? Yeah, I can. Here we go. No, I can't highlight. Yes, I can. Here's one involving force. Here's another one involving force. These two formulas down here, W and P, if you'd like to, you can cross those out. Those are actually in the Science 30 course. So just so you don't get confused and go, whoa, when are we ever going to use the W equals FD or the P equals W over T? I don't believe we use those ones in this class. These formulas down here we've learned. The D equals VT formula and this one here. Before we left for our break, we also learned about this one here, P equals MV, P equals F delta T, and F equals all this stuff here. These were all formulas about collisions and momentum. Does anyone remember which letter we use for momentum? P. P is the momentum unit. Okay. We'll probably have to do a little bit of a review today too. So we've only got a few formulas left to cover. Today, since these two are not going to be counted, we're going to learn these last two formulas here, as well as these collision formulas up top here. And after that, we'll have covered pretty much everything we need to on this page. So your issue then is going to be we got to practice. So, sound good? Well, let's start with our notes here. So this is kind of like the end point of our unit. I've been not talking about how I think that when they wrote this curriculum, the government wanted kids to understand car crashes. I really think that. Because that's the main idea, is that this thing and this thing right here, they're going to collide and crash with each other, and we want to know how much force they hit with, or how long you have to react, or how much distance you need to slow down. So today's topic is all about momentum. So let's do a bit of a review. What is like the non-scientific definition of momentum? Momentum is how much oomph something has, right? Like if I actually asked to put it in like in people words, momentum is oomph. Okay, here. Let's use the examples I did before. Catch. Nice catch. Was there a lot of oomph in trying to catch that pen there? I'd say no. Why was it easy to catch? Well, first of all, I lobbed it at you. Right? Did I give it a lot of speed? You can throw it back if you want, by the way. Here, you throw it harder, though. There we go. Okay, you threw it harder there. If I give it a really good throw, I won't actually throw you, but if I really huck it, that gives it more velocity, right? And that's one part of momentum. If I give it a lot of speed, that gives it some oomph. What's the other part of its momentum? Not just its velocity, but its... Go for it. It's okay. Anyone else want to take a stab at it? Mass, yeah, how heavy it is, right? This pen right here is pretty light. So if I were to huck it at somebody and it hits them, it's probably not going to hurt them. But if this thing right here were a bowling ball and I threw it at them, that might hurt a bit more because it's bigger. Does that make sense? So I think on one of my previous slides, I had an example of different things that have momentum. A bowling ball might be going slow. A bowling ball might be going slow, but because it's so big, it's got momentum. A baseball might be smaller, but when a pitcher throws it at you, it leaves a welt because it's going so fast. Where it's really devastating is like a train. A train is big and fast. So that's this formula that was on the previous, you know how I had your data booklet open there? Momentum is all about these two things here. Momentum is P, and it is your mass times your velocity. The heavier you are times by the faster you are gives you more oomph. That's like the people word for momentum. Fair enough? So what we're going to talk about today then is about conserving momentum, especially through this thing right here. We want to talk about collisions. When things crash into each other, what happens? Go ahead. It's a rolled window at the table there. I want to present a scenario to you here. Anybody play rugby? Just one. Okay, well, can you guys picture, like, say, rugby or football? You got a scenario here where person with ball running this way right here. Person trying to tackle ball carrier coming this way right here, and they are coming for a head-on collision. Right? One of probably two main things happens. This person right here manages to elude them and somehow get through them, or maybe like just run them right over, right? Lower your shoulder. Or this person right here manages to tackle them. Does that make sense? Right? And that's really all about a collision as to who has more force, who is bringing more oomph. And you already intrinsically know this, right? Like if you have to try to tackle the really big person, that's a little bit harder to do, right? Whereas someone who's, you know, a smaller, faster person, they might be a little bit more agile, but like, you know, like the small little person usually isn't the one lowering their shoulder and trucking over the 300-pound lineman in football. You know what I'm saying? It can happen, but that's probably not likely. So I've got three pictures here to try to illustrate some concepts we've got. Here's a good example of baseball, where we've got a collision. The collision is between the baseball that was going this way and the bat, which will, you can't even see that. Let's go with yellow. The baseball, which was going this way, and the bat, which was going this way. Clearly a collision, right? Who wins this fight, the bat or the ball? Well, the bat, right? Because the ball goes back the other way. But here's a couple of reasons why. Who brings more oomph to it? Which is heavier, a bat or a ball? Well, the bat's probably bigger than the baseball is, right? But in terms of also speed, that's one of the reasons why baseball hitters are so fast is that, like, the ability to, like, turn your hands and swing, they are really quick at being able to do that. They bring a high velocity and a relatively big mass, and so it totally can knock the ball back the other way. Here's a couple of bighorn sheep or rams or something about to collide. You know, I don't actually know who's going to win this collision, but, I mean, this guy's coming this way, this guy's coming this way. What's going to happen? Same thing here with your tennis racket. Ball's going this way, racket's going this way. So, do you guys kind of get the picture of what we're trying to get at today? Is we want to talk about who wins a collision, so to speak. Okay. So what I want to talk about here is what's called an isolated system. I don't know whether this is terminology you're familiar with, so I want to kind of give you the briefing from the top. An isolated system, there's actually three types of systems. You don't need to necessarily write this down, but maybe just follow along. The first system is known as an open system. In an open system, this would be like having a beaker with a lid off of it. Can I put more stuff inside? Sure, yeah. The classroom right now is an open system because the door is open. If any of you wanted to leave right now, feel free, go ahead and leave. Because that's an open system. The next type of system is known as a closed system, and that's where you literally just close the door. Right? This water bottle right here is a closed system. Is water going to spill out of it? Well, no, because it's closed, so to speak. I close the door on the classroom. That's a closed system. An isolated system is the most challenging one to achieve because it's like a thermos. The idea behind a thermos is that not only is it sealed, but can heat escape the thermos? Like if I put like a hot beverage inside, you know how it like keeps it warm for a long period of time? That's an isolated system. The idea being that like energy should not be lost all that much. Okay. When we're talking about our physics examples here, we want to consider what's known as an isolated system, where basically the idea is that an open system can have mass and energy leave. An open system, matter has to stay inside because the lid is on. We're talking about a closed system where you should not lose energy or mass. Okay. Here's why that's relevant here. Imagine there's a car crash. Okay, I'll just use these as examples here. imagine there's a car crash, and these two things crash into each other. Okay. For it to work for our purposes here, I can't all of a sudden have a person inside go flying out of the car afterwards. The reason why is that wouldn't be an isolated system because it's not closed. Because if someone like leaves the system, the mass of the stapler has now changed. It used to weigh this much, but as soon as something leaves it, rather than weighing this much, it weighs less. You know what I'm saying here? So that's kind of what I'm going for in this picture right here. Okay. While I'm chatting about this, a good example would actually be this cannon right here. You guys ever watch, like, I don't know, Pirates of the Caribbean? It's one of those like pirate buck-swashing movies with like a cannon here. Why is there a rope on the end here? Anybody know? I found this cool picture here. Why? What happens when you shoot a cannonball? Well, which way is the cannonball going to go? That way. Anybody remember what Newton's third law is? For every action, there's an equal and opposite reaction. Just like shooting a gun, you shoot the bullet that way with your gun, there's a recoil. What happens to the cannon when you shoot the cannonball? The cannon actually goes back the other way. That's why the rope's there, to keep the cannon from like rolling all the way across your ship and like running somebody over or maybe going off the other side of the ship entirely. So these are the sorts of things we want to talk about here. Now, one of the things I want to refer to as the isolated system is it's not fair for my cannon to all of a sudden like break in half, if that makes sense. Or it's not fair for my cannon to all of a sudden have a piece fall off of it. Whatever mass and energy we have has to stay consistent. Okay? For the most part, you don't really need to worry about this. But let me give you a silly example. Let's say we had a roller coaster, and the roller coaster was going to collide with another roller coaster, but halfway through the example, a bird came and landed in the roller coaster. Would that be fair? And I would say, well, no, because all of a sudden the mass changed, and it all of a sudden got heavier by a little bit. So, like, what would be better is if you have a system where, like, it's closed off, and once you're inside the car, you're staying inside the car. You're not leaving. Does that make sense what I'm trying to get at here? So, I'll move on. Well, here's the collisions we're going to talk about. There's three types. There's what's known as a linear collisions where objects separate, a linear collision where objects stick together, and explosions. These are the three we're going to do. And in your formula booklet, they're actually the three that are listed here. If you guys can see that, what we've got is the hit and rebound, the hit and stick, and the explosion. These are the three formulas I want to teach you how to use. And I'll show you this with a couple of, hopefully, common examples. So here's a picture. Let's say you're playing pool. Anybody ever play pool? I have a pool table. I'm a big fan of playing pool. When I shoot the white ball and it hits this orange ball right here, hopefully it's clear that when this ball hits this one right here, the white one and the orange one, they're not sticking together, right? Right? Like what's going to happen is this one's going to hit here, and then maybe the white one will go that way, the orange one will go this way, but they're going to separate after they hit. That's a separating collision. But here's an example of a hit and stick collision. Someone gets rear-ended. Car's going forward, other car goes forward, and eventually crashes into them, and they now move together as like one object because the front end of this car crumpled into that car right there. That's a hit and stick kind of collision. Does that make sense? And then the third one we're going to do is an explosion, where the bullet's going to go this way and the gun's going to recoil back this way. So, like we did before we left for our break, these questions are very much the same. We need to take a word problem. We need to identify which formula to use, identify what numbers go in what spots, so to speak, and then we need to do some math. That make sense? So let's see how I can help with this one. Here's the first one. I'm going to draw a bit of a picture here. There is a white billiard ball. So this will be a white billiard ball, and it's moving to the right. And it hits a black billiard ball. And then what ends up happening is the black billiard ball keeps moving, but like the white one will kind of keep moving as well. Let me see if I can like use some objects to kind of make sense out of this. Okay, so that's at rest. This one's right here. I shoot this one at it. This one goes flying ahead, but this one kind of keeps going a little bit too. So there I can do this with something that can actually roll. That's what we're talking about here. Should I do that one more time? See how that one's at rest, this one's moving? I'm going to have this one hit that one. Now, did this one move? Clearly. Did this one keep moving, though? Yeah, it actually kept moving, right? It didn't move a lot, but like as it went there, it collided right about here, and they like branched offwards. Okay, this is the type of collision we're talking about here. Do it one more time. It's going to hit right about there. See how the tape kept going forward, though? That's kind of the collision we have here. The formula we're going to need then is on the previous slide, and it's in your formula data booklet. It's from right here. We need to figure out whether this was a hit and rebound, a hit and stick, or an explosion. Did the two objects stick together when they were done? Okay, so it's not that one. Did something explode? No. Okay, so it's this one here. It's a hit and rebound. In a way, like the tape hit the what is that, string? But like they bounced off of each other in a way. So this is a hit and rebound. So we can now write out this formula. M1V1 plus M2V2 equals M1V1 plus M2V2. It's kind of a unique formula. I'll walk you through it in a bit. But can you guys take this and write this down on the next slide that we're going to work with? M1V1 plus M1V2 equals M1V1 plus M1V2. I'll start writing it out here too. M1V1 plus M2V2 equals M1V1 plus M2V2. And this is the formula that comes right out of your data book for a hit and rebound, where the two objects do not stick together when you're done. Here's the most important thing about this formula. It is a before and after formula. See how there's an equal sign right in the middle, right? The stuff on the left-hand side is what happened before you started, and the stuff on the other side of the equal sign is what happened after the collision takes place. So to kind of make this example work here, I'm going to throw this thing right here. Does this thing have mass? Yeah, it weighs something. Does it have a speed if I'm going to throw it at it? Okay, so this is its initial speed and its initial velocity. Does this thing right here have mass? If it's just sitting there, though, does it have any velocity? No, it has no zero. Okay, then after that, then I'm going to hit them together. Now, I know they eventually stopped, right? But after they collided, did this thing move with the speed? Yeah. Did this thing move with the speed? It had less speed, though, right? Because it kind of transferred its speed. So let me walk you through where these numbers would go here, then. Do we know the mass of the first billiard ball? Well, yeah, I do. Because right here, see how it says it was 0.15 kilograms? This right here is mass 1. So 0.15 kilograms is mass 1. Do I know how fast it was traveling? Do I know its speed? Well, the white billiard ball that was moving, see how it says it was 8 meters per second? So that's its first velocity. So I actually know that was times by 8. So there's the first bit. Now, what is m times v again? Don't we have a name for that? Didn't I give you a word for that earlier today? Mass times velocity is known as momentum, yeah. So much oomph it has. So this little bitty white ball has, it's a decent amount of speed, I guess. Now let's talk about the next item. So this one is like the white one right here. I'll write this right here. This is the white billiard ball. Well, then it's going to hit the black billiard ball. Do we know how heavy the black billiard ball was? It says it has the same mass. Okay, now this is where you know how I was talking about open and closed and isolated systems here? This doesn't really matter that much to you, but it's a trivial little detail. Once we know its mass, it's not allowed to change again, okay? So like now that this thing's mass was 0.15 kilograms, after it collides, it can't all of a sudden weigh more or less. That's not fair, right? So that's the idea behind a system, is that it's got to weigh the same thing the whole time. So this one's also 0.15. But you know what I'm going to do over here? Is see how there's a mass 1 again over here? I'm going to replace that one with 0.15 and this one with 0.15. Because like after these things collided, after I put the two things here together, this weighs something, right? Does it weigh more? Does it weigh less? No, it makes the exact same thing, right? That's the idea behind an isolated system, is that it shouldn't have changed its mass, right? And this also weighs 0.15. Guess what? It still weighs 0.15. Does that make sense? It's a small little detail, but it's super important because if something lost mass somehow along the way, that would be concerning, or gained mass, right? So, okay, now the black ball, before we started, how fast was the black ball traveling? No, the white one was traveling 8. How fast was the black one traveling? No, 0. Because didn't it say it was at rest? That's velocity 2, and that's nothing. 0. So let's do a quick recap here. One of the objects weighed 0.15. It was moving 8 for speed. The other object also weighs 0.15, but it wasn't moving at all, so 0. Okay. This is all before. Well, then it collided. So then after it collided, it weighs the same amount, because I just talked about the whole thing, is after it collided, it still has the same stuff there. Okay. But then how fast did the white ball move? Well, actually, it tells you that. Doesn't it say the white ball now is moving 2.5 meters per second? So that means this V1 right here is now 2.5. Let me illustrate that for us in this example here. So, white ball, black ball, at rest, and I'm going to shoot this one at it, right? This thing's I'm going to shoot it with 8, okay? It kept moving afterwards though, right? Because it went in with 8, it hit this guy, but it kept going, but it only went forward with, say, like 2.5. Does that make sense? So afterwards it was 2.5. Our question then is we want to find the velocity of the black ball, which will be this one right here, black, which means we want to find this V2. So here I've kind of finally put the equation together. These are the most challenging ones because there's numbers everywhere, right? And this is where I think, this is why kids get so frustrated with physics, is that it's like, whoa, like there's an M here and a V here, an M here and a V here, and if you can decipher and interpret what's happening, that's half the battle. It really is. So let me just make sure I'm clear on this. The white ball weighed 0.15. It was traveling 8. Was, keyword. The black ball weighed 0.15. It was traveling 0. Was being the keyword. Then after they bumped into each other, the white ball still weighed 0.15, but now the white ball is only 2.5 because it slowed down. Where'd the rest of the speed go? Well, it must be going to this one right here. So, how to do so far? Are you guys able to follow where all the numbers like went to? Okay, that's stage 2, right? Step 1, pick the right formula. Step 2, put all the numbers in the right spot. Gesundheit. Step 3, the hardest part, we got to do our math. We need to try to find a way to get this V2 right here, this velocity, algebraically, like mathematically, by itself. So let me give you some advice on how to deal with this. First piece of advice, whenever you have numbers that you can multiply and add to each other, you may as well do that. Okay. So grab a calculator. What is 0.15 times by 8? That shouldn't be too hard to do. What is 0.15 times by 8? 1.2. What is 0.15 times 0? I don't need a calculator for that one, right? 0.15 times 0 is going to be 0. Oh, wait, over here, what is 0.15 times 2.5? Wait, and then this last one right here, I kind of just leave them next to each other. It's going to be plus 0.15 times v squared. So I kind of have to leave that one with where it's at. Okay, quick algebra lesson. We need to get this v squared right here all by itself. And so I need to get rid of a couple of numbers. Specifically, I have to get rid of this 0.15, and I have to get rid of this 0.375. Okay. Does anybody know how to get rid of the 0.15 when it is being multiplied by v squared? How do you undo a multiply? Yeah, that's exactly it. That's one of the things we'll have to do. We're going to have to divide both sides by 0.15. However, there's one more thing we have to do. See this 0.375 that's right here? It's being added. How do you undo an add? Subtract. Okay, here's the important question though. Which one do you do first? Should we subtract first or divide first? It's actually to subtract. And here's how I find is useful to teach kids, but you guys have ever heard of BEDMAS, right? BEDMAS? BEDMAS? Okay. Well, when you're doing algebra, you actually have to do SAMDEB. Backwards. Because like what we're doing here is we're undoing all of our steps. So you know how in BEDMAS you got to do brackets, exponents, divide, multiply, add, and subtract? When you're doing algebra, you do the exact opposite process. So if you ever want to know which way to do it, it's actually SAMDEB. So to answer the question, should we do our divide first or a subtraction first? We got to do a subtraction first. So let me see if this kind of makes sense to you guys. We need to get rid of this number here, the 0.375. And the way we'll do that is we're going to subtract 0.375 on both sides. If I show it like that, is that something that's kind of familiar where you like do the same thing to both sides? Because this will now go away. So you guys help me out with the calculator. What is 1.2 plus 0? Well, that's dumb. Minus 0.375. 1.2. 0.825. That makes sense to me. Everybody okay with that? So 1.2 plus 0 minus 0.375. And that will then give us, now this stuff here goes away, so all we have left is 0.15 times by V2. Last step. We now need to do the opposite of BEDMAS. So we took care of our subtraction. We took care of our addition, because right over here, didn't we do our addition as well? I don't actually have to do any multiplying. So last step, do I have to do any dividing? Well, yeah, I have to divide both sides. Divide by 0.15 on both sides. So if I divide 0.15 on both sides, now I'll have V2 by itself. So, need some calculator help again. What is 0.825 divided by 0.15? It is 5.5, yeah. Has everybody else that's tried that in their calculator, did they get the same number? Did you get 5.5 when you did that? Okay. I want to talk about this for a second here. How fast was the initial guy traveling? 8. Now, the other guy was traveling 0. How much net speed was there? Well, 8 plus 0 is... No, 8 plus 0 is 8. Okay. So when we started, one guy had 8, the other guy had nothing. Now, after we were done, didn't one of them have 2.5? What's 2.5 plus 5.5? Also 8. Yeah, because really what happened is, if I can go back to my example here, this guy comes in with 8 for speed. This guy's got nothing, right? After we're done, they collide. This guy right here gets 5.5. This guy gets 2.5. 5.5 and 2.5 still adds up to 8, right? So the initial speed that you went in with is the same for both. Now, here's the only reason why that worked, though. They were both the same mass. If one of them was heavier than the other one, that would have changed things. But because everything weighed the same amount, then it actually ended up being that the speeds just kind of added to each other. How did I do? In terms of my first example, could you follow that? Okay. One of the things I'll tell my students all the time is that I think there's 3 levels of understanding. Okay. The first level of understanding isn't actually a level at all. The first level is I talk to you, and it goes, and you're like, yeah, I got that, Chris. Okay. If that's you, please tell me. Okay. I will try to help you. Okay. Okay. Maybe you don't want to tell me right at this second, but like if I lost you, you got to tell me at some point so I can help fix. So that's level 1. Level 2, you watched this and you were like, yeah, I get it. You know, if somebody else is there to work with me, I think I can do it. That's level 2. My goal, I got to get you to level 3. Can you do it by yourself? Okay. So I need you guys to each internally kind of figure out where are you at. Are you at the level where it's like, and you're like, yeah, I get it. Please tell me, okay? I'm not scary, okay? Level 2, you can watch me do it. Level 3, how do you get from level 2 to 3, by the way? Practice, yeah. So let's try another one. Here's a scenario here. You've got 2 balls of clay. I don't know, whatever. 2 balls of clay. One has a mass of 2.3 kilograms, and then the other one is 5.6 kilograms. In this example here, the 2 things that hit each other are now different weights. Just to throw a little twist in there. Here's the difference, though. Now they're going to stick together. See those two words right there? That now gives away which formula we're using. If I can try to do an illustration here, this won't work quite as well, but I can make it work a little bit. You know how the first time I hit them, they hit each other and they bounced apart? I'm going to do this now. I hope this works. I'm going to put the sticky side of the tape on there. And now they're going to go. Ah, it didn't work. It's going to do that. And now they're stuck together. Does that make sense what I'm going for here? Kind of like the car that gets rear-ended. So, as soon as I see those words stick together, thing number one I need you guys to be able to do, figure out which formula to use. So go back to your formula sheet section and find this formula here. M1, no, now we need this one here. M1 V1 plus M2 V2 equals bracket M1 plus M2 V1 and 2. I have to help you with this one here. So write this formula down here, and then we'll start on that in a second here. So M1 V1 plus M2 V2 equals M1 plus M2 in brackets, and then V1 and 2. M1 V1 plus M2 V2 equals bracket M1 plus M2 V1 and 2. That's the formula. Anyone have any idea why M1 plus M2 are put in brackets? What's different about this scenario than the last one? The two objects got stuck together. And that's why this is now in brackets here, is that the two masses of the two objects now have to get added in a bracket. So now how we talked about bed mass? I'm going to write that down again. We're going to have to undo bed mass and do SAMDA. But before I get that far, though, I got to start plugging some numbers in here. So, is everybody okay with understanding which formula to use? Hopefully it's clear because I told you they stuck together. So, let's plug some things in here. The blue clay ball was 2.3 kilograms. Why don't I make this M right here be 2.3? The red one was 5.6. Where's the 5.6 go? Yeah, let's make that 5.6 right here. Yeah, there we go. M2 5.6. Now, hang on a sec, though. I can still use that. Remember closed system? The idea being that, like, the masses should not change after they collide. So, you know, these two masses right here, I need to actually add them together. 2.3 plus 5.6 need to get added together. So I can actually throw mass in here, 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 and here for my masses there. If you can kind of follow that there. All right, next step here. I'm missing a few numbers there. I still haven't dealt with this V, or this V over here. Well, I mean, doesn't it give me a velocity right here of 12 meters per second? Well, let's make that be this one right here, 12 meters per second. Because wasn't the blue one, the 2.3, the blue one is 12? And then it says the red one is 8.1. Except there's one little mistake here. It's all about direction. I actually didn't do this one properly here. I didn't realize this. But this is more of a scenario like this, where this one's coming that way, but this one's coming this way. Does that make sense what I'm saying here? And so they're actually going opposite directions, and when they're finished the opposite directions, they're going to hit each other, and then they're going to kind of stay together as a group. So imagine for a scenario that there's a collision at an intersection, two cars hit each other, but like after they hit each other, one car ends up like winning a little bit, but like they're smushed together now. You get what I'm saying? That's our scenario. Here's why that matters then. I have to throw in a negative sign. I'm going to make this 8.1 be negative 8.1 because it's going from the other direction. Does that make sense why one's negative? Because this guy's going forwards, but the other guy's coming the other way. So I got to throw a negative sign on there. this one was going to the right, this one's going to the left. Okay, now the only other thing I need to work with now is this v1 and 2, which is really what I'm being asked to solve for. Determine their final velocity. Aren't these two things now stuck together? So v1 and 2 is really the speed of both of them, right? However fast the one car is going is the same speed as the other car is going. So we've now finished step 2. We've identified the formula and we've plugged numbers in everywhere. Now for the math part of it, we need to try to get this v1 and 2 all by itself. So I'm going to recommend, let's start by putting some numbers together that we can. So if you got a calculator, 2.3 times 12, let's start with that. What is 2.3 times 12? 27.6. Cool. Okay, then I need to have 5.6 times negative 8.1. Don't forget that negative, it's super critical. 5.6 times negative 8.1. Negative 40. 36. You else get that? And then over here, this stuff here is in brackets. Let's add these together. What's 2.3 plus 5.6? I can do that in my head. 7.9. And then we're timesing that by v1 and 2. Because it's written directly next to it. If it's written right next to it, that implies that it's being multiplied. You know what? I think we can probably still do one more thing here. Before I even try to isolate for this v over here, couldn't I take these two numbers right here and subtract them from each other as well? So what's 27.6 minus 45.36? It's got to be negative, right? Because the 45 is bigger. $27.6 subtract 45.36. Okay, and that's going to equal 7.9 times v1 and 2. Now, right here, I had written some brackets around it. Because there's nothing being added inside of it anymore, I really don't need those brackets anymore, so I'm just going to stop writing them. Here it was really important because these two numbers had to be added together. But now that they've been added together and merged together as this one thing here, those brackets really are no longer needed. So. All right, now we're to the algebra stage. We need to get this v1 and 2 all by itself. How do you get rid of the 7.9 when it's being multiplied by it? Divide, yeah. I don't really need to worry about BEDMAS or SAMHSA because there's really only one thing I have to do. I have to undo the divide. So divide both sides by 7.9. Divide u by 7.9. v1 and 2 is 17.76 divided by 7.9. I have this number here. I have negative 2.248 maybe. Why is it negative? Why is it negative? Let's go back to our scenario here. One guy's coming this way. The other guy's coming this way. Now I think we chose for this one to be the positive one and this one to be the negative one. You know what the negative tells me? It tells me who wins. In this scenario here, that's what happened. In terms of the collision, as they came in towards each other, sorry, I'm kind of in your way. As these two things come in towards each other, see how like this one kind of bounced back like that? There, that was best, right? So the negative just tells us which way it went. If the right was positive, then these things must have been moving to the left, because you know how we made the 8.1 negative by being left? This must mean he's going left. So now we know which one won. The red one won. But honestly, doesn't that make sense? Think about this for a second here. The blue one, how much oomph does it have? It brought 27 oomph to the table, because it had a mass and a speed. And in terms of its oomph of momentum, it brought 27 to the table. Does that make sense? How much oomph dough did the other one bring? Well, I know it wasn't going as fast. It only moved 8.1, so it's moving slower, but it's bigger, right? Like this guy's heavier. It's 5.6 for heavy, and it's only got 8.1 for speed. So who had a bigger oomph? The first one, this one here was blue. This one here was red. Who provided more oomph? Well, red provided more oomph. Does that make sense? So that's why the red one wins this collision. If you're thinking about rugby or football or whoever's tackling, right? As two things come and tackle each other, whoever comes with more oomph, either it's going to go like this or it's going to go like this, right? If you watch football, like at the goal line when you're trying to score a touchdown, that's where it really matters, because if they're going to collide, right? If he can fall forward, he'll score a touchdown. But if he gets pushed backwards, then they stop him, right? This is literally where physics and sports collide. No pun intended. Right. Did that make sense? Like, anybody, you guys able to follow that? This is challenging. Like, this is why kids hate physics a lot. But if you can follow this, then I just need to give you guys some practice on this. So, I should probably do one more thing here, I guess. I should add a unit to it. The units would have been meters per second, I guess, because that's a speed unit. So I guess in a way, now we know that it was the left that wins. If one was going this way and one was going this way, so this guy is going right and this guy is going left, it wins, though the left one ended up winning the fight, I guess. Let's try another one. A bullet is fired. Pause. As soon as something is fired, which equation are we probably using? Okay. So step one, go right down the explosion equation. So it's in your data book, or it's way back here. It is bracket M1 plus M2, V1 and 2. Bracket M1 plus M2, V1 and 2. And then it equals, where is it? M1 V1 plus M2 V2. M1 V1 plus M2 V2. So step one, you got to figure out which of the formulas to use. How many formulas are on that sheet by now? We must have like probably 10 to 15 we're probably getting up to. Oh. And that's probably the biggest challenge as you go along, is sometimes you got to first figure out which formula we're even going to use. Anyone want to hazard a guess as to why, in this case here, M1 and M2 are together in brackets? What happens when you fire a gun? How does it start? Isn't the bullet inside the gun? So don't you really have like two things stuck together? And then after you shoot the gun, the bullet goes one way and the gun goes the other way. So in a way, what we've got here is one thing that was stuck together. These masses are stuck together. And then afterwards, one goes this way and one goes that way. So maybe even the formula kind of makes sense as to where it came from. Oh, let's throw in some numbers here. Do I know one of my masses? Well, yeah, isn't the bullet that many kilograms? So let's make this one be 0.050 right there. And if I'm being consistent, then over here, let's make that mass also be 0.050 as well. So the bullet, very small. What about the gun, though? Well, the gun is 5 kilograms. Does it make sense then to make this mass right here be mass 2? And then over here be this mass 2 as well? We're starting to piece this together. So this mass went here, this mass went here, same number went there again, same number went there again. It says the velocity of the bullet is 275 meters per second. Where's that going to go? Which one of these two things right here is the bullet? Yeah, so I should make this one right here. I'm going to write it below there, but I'm going to make that 275 because this is your bullet. But we know from Newton's third law that if the bullet goes one way, the gun goes backwards the opposite way, like the gun recoils. We're still missing a number, though. There's actually a sneaky hidden number sitting here. I'm going to write it out for you, and then you guys can maybe try to explain to me why it's this value. I actually know what V1 and 2 is. This number right here, 0. Why is it 0? When you start shooting your gun, and I'm standing here with my gun in my hands, is the bullet moving yet? Is the gun moving yet? When I press the trigger, and the bullet goes that way and the gun goes that way, sure, now it's working, right? Does that make sense? Like, as I'm literally sitting here with my gun waiting to shoot something, nothing's moving yet. Not until after the explosion happens. So it's very sneaky, but your first velocity was actually 0 in this example here. And what we don't know is v2, which is the recoil velocity of the gun. So this was step 2. We first found our formula, step 1. Step 2, we got to plug all the numbers into the right spots. It's hard enough as it is too. Step 3, now we got to solve for v2 right here. So let's combine some numbers wherever it's logical. So for example, what is 0.050 add 5, but then times by 0? Yeah, because really, isn't anything times by 0 going to be 0? So if I add these numbers but times by 0, this whole side is 0. All right, next help. I need to do 0.050 times by 275. So 0.050 times by 275. This number right here, when I put it together, gives me 1375. And then I have 5.0 and V2. Lose anybody on that step there? Lost you? Yeah. That's a 275 right there. I didn't have enough room to write it next to it, but you see how it was m times v? This is the mass and that's the velocity there. And times those together gave me that number. Thank you for asking. Anybody else have any issues with where numbers kind of randomly show up from? Because I know that loses kids a lot. Okay. Next step then. We need to get v2 by itself. I have to do two things. There is a multiply sign that I have to divide by, and there is an add sign I need to get rid of. Which one do I get rid of first? Yeah, you have to do subtraction first. So I'm going to subtract 13.75 from both sides. So if I do that, hopefully you guys can follow this. You now have on this side here 0 minus 13.75 gives you minus 13.75. And then on this side right over here you have 5 times v2. And then for your last step, you have to get rid of the multiply. To undo a multiply, you divide. So I divide both sides by 5. So to get velocity 2 by itself, we need negative 13.75 divide by, that's 5.0 by the way, that was pretty ugly writing on my part, I'm sorry, 5.0. So let me know if you can't get this number here, because that's what I got. I got 2.75, negative 2.75. Right here or over here. So I used to have, I'll write it over again. It used to be 13.75 equals 5.0 times by V2. And then what I did is I divided, the way I show my divided bys is I do line 5.0 and line 5.0. That's how I show it. If you wanted to do like divided by, that works too, I guess, there. Because then I got rid of all that because dividing by it makes it go away. And then I have then this one divided by this one. Does that make sense to you? Okay, let me know. I'll slow down if you need. So yeah, divide by 5.0 and then divide this side by 5.0. And let me know if you don't get 2.75. That makes sense? Let me know if I go too fast. I will slow down. Okay, let's talk about a couple of thoughts here. Why is the number negative? Well, yeah, because isn't the bullet the thing that's going forward? Isn't the gun recoiling back into you? That actually makes perfect sense. Right? One thing I should point out is the units for this are meters per second. That's the standard physics unit. Standard physics units are kilograms and meters and seconds. So if you ever get grams or kilometers and hours, we got to move those ones. Okay, I did 3 examples. That makes sense? If you can do this, you've got it. Okay, like this is like the hardest thing we do. Can I ask for one favor from you guys though? If you are lost, please tell me. I will try to help. It may mean we have to have a conversation in a couple of weeks. I want you to try it about whether or not 20 is actually the right course for you. Because if I lost you here, it may be too hard, at least at this point. Okay, but if you are lost, please do not just sit there and go, I'll get it later. Like it's not gonna happen like magically in 2 weeks, probably. Like you have to work and practice at this. Okay, so please let me know. I don't think I'm a scary person to ask. So. Okay, I got to show you two more formulas, then we're going, okay? We're almost done the unit. Here's the last two formulas. We've talked about momentum. Momentum is how much oomph something has. But there's another word we sometimes use known as energy. Certain things have more energy than other things. This is a formula right here for what's known as EK. EK, stay with me, guys. I know it's almost the end of the day and I'm talking for a long time, but try to stay with me. EK is known as kinetic energy. Okay? Kinetic energy is the energy when something is moving and being thrown. And so if you ever want to try to calculate something's energy, here's the formula. 1/2 of mass times velocity squared. It's very similar to momentum in terms of how much oomph you have, but it's now in energy units. Okay? And then I have another formula here where it's known as potential energy. And I want to illustrate that here with a simple thing here. If I let go of this pen, it's going to fall, right? Why is it going to fall? Well, it's going to fall because it has what's known as potential energy, energy due to gravity. Gravity will make this thing fall. And that's why I see in the corner there's EG. That's energy due to gravity. Things fall based on three things. Mass, the fact that gravity exists, and how far they fall. If I drop this from here to here, how much energy is that? Well, it's not a lot because it didn't fall very far. If I drop it from here to here, see how it has a bigger, louder bang to it? That's because it fell from further. So height is one of the factors. Another factor is mass. If I drop this, or if I drop that, why did one make a louder thud? Due to mass. So the three factors in terms of gravitational energy are mass, height. Does anyone remember what G is, though? It actually was from a previous section we talked about. Do you know how much gravity affects things on Earth? 9.81. Okay. So here's my last thing. I want to show you how to use these two formulas. These are for energy. Energy is not momentum, but it's very closely related. So let's do an example here. Oh, actually, this is the example we're going to do in the egg breaking lab. So actually, why don't we call it quits here for today? And tomorrow I'll show you how our lab is going to work for egg thing. But here's the basic rundown. We are going to put an egg in a bag. You're going to build a helmet for it to try to protect it. We are going to get some sort of wall for it to crash into, and we're going to swing it into the wall. Okay? And I'm going to show you how to calculate things like force and energy and momentum and time and distance using all these sorts of formulas. So these are all the things we're going to learn how to calculate. Gravitational energy, speed, momentum, deceleration. Does that make sense? And so hopefully through this one example, I'll be able to show you how to use all of the formulas we have on that sheet. So, but I think we probably should call it a day for now because this is going to take us a little while. So, do you guys have any questions of me? Okay, one last thought, and then you guys can probably, not pack up and go, but we can start getting to that stage here. There are 4 tasks then that we talked about. 2 activities, 2 assignments. Okay, I will work on them with you as much as I possibly can, but I got to be honest, you guys are going to have to do some homework, okay? I know that's not necessarily something maybe has been a strength in the past, but like if you do want to be successful in a course like a Science 20, maybe Science 30, you're going to have to do a little bit of work outside of class time. So now if you get stuck, that is fine. Like I get it if you get stuck. Come find me guys tomorrow during flex time. I will sit down and work with you guys on this stuff if you need. Okay? But we have effectively finished this unit, okay? There's nothing more to learn in physics, really. So if you can master what we've been talking about, we're good. So here's the plan again. Tomorrow we're going to do some work time. Wednesday we're going to do the egg cracking competition. Don't have to bring anything, just show up. Thursday and Friday we're going to write some quizzes. If you do well on the quizzes, yay, they count. If you don't, well, they don't have to count. But you do have to count something, okay? You can't literally omit everything we do. You got to count something. And then next week, Tuesday, we're going to write a unit test. Sound good? Okay, I'll turn off the recording. You guys have 10 minutes to kind of work on stuff. Maybe don't pack up just yet. Maybe look over your assignment or your activity and see how much you have left. Because you do have 10 minutes left.